Okay guys, welcome to Unit 4. You may have noticed we skipped Unit 3. That's because it seemed like the right thing to do. Unit 4 is going to deal with quadratic functions and equations, and in the very first section we're going to talk about transformations, which is nice because we just did a lot of transformations at the end of Unit 2. So a lot of this hopefully is going to seem like review. So the objective today is we're going to be able to identify and graph quadratic functions. Okay, quadratic functions. A quadratic function gets graphed in the form of a parabola. Okay, a parabola is this curvy U-shaped, however you want to describe it, but it's a parabola. We wrote quadratic equations in Algebra 1, and we used this form: ax squared plus bx plus c. The big deal being that a is not equal to 0. Okay, the graph of any quadratic is transformed based on the parent function, which is just y equals x squared. Okay, y equals x squared is the parent function. Some of you may have already looked at that in class. And so we looked at the parent function of a quadratic function, at least my class did. So vertex form, so this is like the standard form of it. Vertex form is a times the quantity x minus h squared plus k. And that shows us all that should look just like the absolute value stuff, except for we have this little 2 up here now. But it has the same effect, okay? The axis of symmetry is down the middle again, just like absolute values. The vertex is h and k, just like absolute value. So a lot of this should seem really familiar, okay? This is the parent function down here. Let's take a look at some examples. So what is the graph of f of x equals 1/2 x squared? So the fact remains that we can still just put in some numbers and get out some numbers, okay? So you can always just make a table. This hasn't been shifted up or down, so it's at 0, 0. And then we get points 2, 2, and we get points 4, 8. And here we are ready to graph the curve, making sure that there's arrows on the end. That's important because it does go forever, okay? So no problem. So let's take a look at this one right here. So what is the graph of f of x equals negative 1/3 x squared, okay? So take a second. Well, first let's notice some things. We have 1/3, so okay, so that should remind us that it's a compression. And then this negative sign here is going to do something, and hopefully you're thinking, I think that's going to reflect it over the x-axis, just like it did in absolute values, and you would be correct. So let's take a second. Pause the video, and go ahead and sketch that graph. Pause the video now. Alright, so here's my table of values. You'll notice that I picked numbers that I knew were multiples of 3 so that they'd work with the fraction nicely. So negative 6 squared is 36, negative 1/3 times 36 is negative 12, and so on. So there's my numbers, and over here is just my sketch of the graph. Take a look at part B. What can you say about the graph of the function of f of x equals ax squared if a is a negative number, and explain? And you want to have something there along the lines of, that's a reflection in the x-axis. It looks upside down, something, so that we can see that it changes. It's a mirror image of the parent function as far as that goes. Okay. Key concept here: the reflection, stretch, and compression. All those things are the same as what we've just done with absolute values. Okay. If the x squared is negative, then it's upside down. If a is greater than 1, it stretches it. If it's between 0 and 1, it compresses it, just like we've been doing. If a is greater than 0, the parabola opens up. Okay, so if the number out front is greater than 0, the parabola opens up, and it therefore has a minimum value. Okay, a number that it cannot go below. If it opens down and a is less than 0, it has a maximum value that a cannot go above, and that value is at the vertex. Okay. So graphing translations. So now if we want to graph each function, how is each graph a translation of f of x equals x squared? So if we look at f of x, or g of x equals x squared minus 5, it's literally been shifted down 5 units. That's it. If we looked at here, it's on the inside. That's shifted right 4 units. This should seem very, very simple. Okay. So when we graph these two, you can pause the video and practice graphing here if you want, but I'm really more concerned with what's happening. So how is this translated, this part A? How do we think that is translated? Hopefully you're in the process of writing down that it's been translated, it's been shifted up 3, or translated up 3. And here, this has been translated or shifted left or right, left 1. Okay? That's it. The vertex form f of x equals a times x minus h squared plus k gives you information about the graph of f without drawing the graph. Okay? So we get sort of all this information in vertex form without having to draw it. We know whether it has a minimum or a maximum. We know all these things. So we want to take a look at this one, for example. Look at 3 times the quantity x minus 4 squared minus 2. What are the vertex, axis of symmetry, max or min, domain, and range? So let's start with what's the vertex. Well, the vertex is hk, so that's going to be this value, and it's positive because the general form has a negative. So it's positive 4, and it's down 2, so the vertex is negative 4, negative 2. We got that. That's supposed to be a check mark. That's kind of unbelievable. There we go. The axis of symmetry is x equals h, and here h is positive 4, so we got that. A is greater than 0, so the parabola opens up and has a minimum value at this number, at this number. So negative 2 is the minimum value. The domain, think about it, all the x values are the domain. Well, this is all parabolas. Remember when we made the point about them having arrows on the end? They go forever. So the x values are all real numbers. The range are all real numbers greater than or equal to the minimum. If it were at a maximum, it would be less than or equal to the maximum. But here it has a minimum, so it's greater than or equal to negative 2. So what are the vertex, axis of symmetry, max and min, domain and range for that function right there? Go ahead and pause the video here and get those answers. Go. All right, so let's start with the vertex. The vertex, hopefully you got, is negative 1. Let's do a different color. Hopefully you got as the vertex was negative 1 and 4. The axis of symmetry is at x equals negative 1. Does it have a minimum or maximum? This is negative, so it's going down. So it has a max. Okay, it has a max at 4. The domain is all real numbers. And the range, okay, the range is going to be all real numbers less than or equal to the maximum, which is 4, okay? So y, we can look at this, y is an element of the reals such that y is less than or equal to 4. We'll talk more about that. All right. So we can use the vertex form of a quadratic function to transform the graph. We can stretch or compress. We know if it's been reflected. We know where to shift it. No problem. Okay. Key concept here. Okay. Key concept time. This talks about the movement left and right as a horizontal or vertical shift. And really, guys, this stuff is just like the absolute value stuff. So hopefully this is making sense. So what is the graph of f of x equals negative 2 times the quantity x minus 1 squared plus 3? Well, we want to identify some things like these constants a, h, and k because we can use those. We know it's going to, you're almost like, just figuring things out. We know it's going to open down. We know that the vertex is at positive 1, positive 3. So if we were graphing this, there's that. We know that if you look right here, we want to plot 2 points. So we can plot, if f is 2, you plug that in and you get 1. So this was at 1, 3. That's not a very good. Let's do this. Jumped pages on you there. So if we were gonna look at this graph, and it's obviously it's this right here, guys, but this is how it looks at a piece of time. So we get the vertex is 1, 3. Then we put in a point like 2, for example. You find out what it is. And it ends up being 1, so 2, 1 is a point. Well, symmetrically, the other point is there at 0, 1. Okay? We know the line of symmetry is there because of this number. And from there, we can draw it. That's it. Boom, boom, and we just drew the curve. What steps just a piece at a time. And again, just like the absolute value stuff, this should look very familiar. What steps transform the graph of y equals x squared to y equals negative 2 times x plus 1 squared plus 3? So what's happening? So we're looking for it's shifted up 3 and left 1 and reflected and stretched. So that's what we're looking for. So reflected, yes. Stretched, yes. 1 unit to the right and 3 units up? No, that is not 1 unit to the right, so it's not A. Okay? B, stretched by a factor of 2, translated 1, but it doesn't have the reflection, so it can't be that. Reflected, yes. Translated 1 unit to the left, yes. 3 units up, yes, but it doesn't have the stretch, so that's not correct, so the answer is D. Stretched by a factor of 2. Reflected, translated 1 left and 3 up. And that's it. So, what translates this one? Go ahead and take a second, pause the video here, and get an answer. What is the translation that is going on in 4? Pause the video now. Hopefully you have something like this. Maybe it doesn't have to be in this order, but it's stretched by 2, translated left 2, and down 5. All right. We can use the vertex from a quadratic to model a real-world situation. So the picture shows the jump of a dolphin. What quadratic function models the path the dolphin jumps? So here's the dolphin jump. We get the vertex right here at 3, 7. Okay, it's right there. So that's the H and the K. We know that the A is going, well, we can solve for it, really. Choose another point from the path. So 9, 4, there's another point. So we plugged in 9 for the X and 4 for the Y, and we have H as 3 and K 7. So we plug all those in and we solve for A and get negative 1/12. And then this right here is the quadratic function or quadratic equation that models a dolphin's jump. Isn't that exciting, guys? You're going to look at the beach, totally different. So let's take a look here. Suppose the path of the jump changes. So the axis of symmetry becomes x equals 2. The height stays the same. If the path jump also passes through the point 5, 5, what quadratic function would model this path? So let's do this one together. So we're looking at, and again, I think it's a good idea always to write down the formula that we're working with. Okay? So once we have that, we can sort of plug in what they've told us. Okay? They said that the x is 2. Okay? The axis of symmetry, anyways, is 2, which that's our h value. So I know that this is going to be x minus 2. Okay? Squared. The height stays the same. So the height was 7. Okay? So this is plus 7. We don't know the a. That's what we don't know. Okay? So what we're going to do is we're going to plug stuff in and figure out what the a is. I'm going to put that over there for a second. And then we're going to say, all right, well, we have a y value at 5. They told us that that is on the curve. The a value we don't know. The x value is 5. This is minus 2 squared plus 7. Okay? Don't mind that. Go away, calculator. Okay, so now let's solve for a. We get 5 equals a times 9. That's 5 minus 2 is 3. 3 squared is 7. Or 3 squared is 9. Plus 7. I'm going to subtract 7 from both sides, and I get negative 2 equals 9a. I divide both sides by 9, and I get a equals negative 2 ninths. So now I've solved for my a. I'm going to put that there, and that is my answer. Okay? Negative 2 ninths is my a. So f of x equals negative 2 ninths times the quantity x minus 2 squared plus 7 is my answer to that question. That's it for the notes, guys. I will see you next time. Make note of any questions or anything you want me to go over so we can start this next unit off really well. See ya.